today I am going to discuss plane kinematics of rigid bodies. Till now we have discussed kinematics of particles. Now a rigid body is composed of a number of particles. In fact, you can say that it may consist of infinite number of particles. However, that rigid body has fixed degree of freedom because all the particles are not free to execute their motion at their will. They are all constraints, that is, say distance of two particles on the body remains same. So, now we discuss about the kinematics of rigid body, but we start with a plane motion in which the rigid body is moving in a plane. Therefore, it has got 3 degrees of freedom. We can fix up a point on the rigid body, say mass center, and say what is the x coordinate of it, what is the y coordinate of it, and then what is the rotation of the body about this point. So, you have x, y and theta. Therefore, we say rigid body executes plane motion when all parts of the body move in parallel planes. We generally consider the plane of motion to be the plane that contains the mass center, and we treat the body as a thin slab with motion confined to the plane of the slab. So, actually that we will take that mass center and pass a plane through that, the motion will be taking place in that plane. The plane motion of a rigid body may be divided into several categories. We discuss some of these. Translation, it is a motion in which every line in the body remains parallel to its original position at all times. There is no rotation of the lines in the body. In translation, we have two types of translations. One is rectilinear translation, in which all points in the body move in parallel straight line. Then we have curvilinear translation, in which the points do not move in parallel straight lines, but they move in parallel curves. Now, the body may move in a circular path also. For example, this body here, okay, this one is moving on a circular path, that red circle, and this is the thing, but body is not rotating, body is not changing its orientation. So, therefore, this is not a rotation, rather it will be called translation. On the same path, if the body moves this thing like this, so that it is radially, that its orientation is changing, then this motion will not be called translation, like this. So, in rectilinear translation, all points in the body move in parallel straight line. Now, see this animation here, the body is moving in parallel straight line. See this again, yeah. Now, if we know the velocity of any one point on the body, we have known the velocity of whole body, because all the particles are moving in the same way. So the velocity of all the particles is same in direction as well as magnitude in this case. Now in curvilinear translation, all points move on congruent curves. So this is an example of curvilinear translation. However, even in this case, the velocity is same for all particles. So in this case, the velocity may be changing. The velocity here may be small, then it is this thing, body may be accelerating or decelerating, that is a different issue. But velocity of one particle is same as the velocity of any other particle on the body. So this is example of that curvilinear translation. Now notice that in translation the motion of the body is completely specified by the motion of any point in the body, since all points have the same motion. The velocity of the translating body can vary with time in both direction and magnitude. However, the velocity of that all points will be same. So generally we speak of the mass center. We specify the velocity of the body by the velocity of mass center. In translation, the velocity of mass center will provide the velocity of any point on the body. Now we discuss about rotation. Rotation about a fixed axis is the angular motion about the axis. Consider a point O and draw a perpendicular to your screen. That is, the axis of rotation is perpendicular to your screen. Now see the following animation for obtaining the rotation of the rod about the axis passing through point O and perpendicular to the plane. Now in this case, this line does not remain parallel like in translation. Instead, it rotates by an angle theta. This is the initial position. With respect to the initial position, it has rotated by theta. It follows that all particles move in circular paths about the axis of rotations, and all lines in the body that are perpendicular to the axis of rotation rotate through the same angle in the same time. Here it is rotating. Now all the particles are moving in a circular path. Also, all the particles which are in this line have rotated by theta. That means this line, if we consider this line, this is theta, this is also through the same angle in the same time. Now, general plane motion of a rigid body is a combination of translation and rotation. A body can have translation, it is as well as rotation. You can reach to some point and translate the body to some point, then you rotate, or you first rotate and then translate, you will get the same thing. So it is general plane motion of a rigid body is a combination of translation and rotation. If a rigid body moves so that along some straight line all the particles of the body or a hypothetical extension of the body have zero velocity relative to some reference, the body is said to be in rotation relative to this reference. So that if a rigid body is moving, now if it is moving about this point, if it is rotating about this point O, and you draw a perpendicular to the plane passing through O, then on that axis all the particles have zero velocity. Therefore, the body is rotating about this point O. Consider other case, the body may be rotating about this point O, which is not in the body. It is some, hypothetically, if we extend the body up to that point, it is rotating about this point. So therefore, we can have axis of rotation outside the body also. In that case, we make a hypothetical extension as if there is a body and its particles follow the same kinematics. The line of stationary particles is called the axis of rotation. So when the body rotates, there is one axis of rotation. The rotation of a rigid body is described by its angular motion of any straight line of the body. We see any straight line. Why we say any straight line? Supposing there are two straight lines, 1 and 2 in the body, which are at an angle of beta with respect to each other. This is a body, line 1 is there, line 2 is there, both are making an angle beta. Now take a reference horizontal line. At any instant of time, the lines make an angle of theta 1 and theta 2 with a fixed horizontal line which is taken as a reference. So this is theta 1 and this is theta 2. So this is what it is doing. Now in the figure, theta 2 is equal to theta 1 plus beta. Because the beta is angle, you can see theta 2 is equal to theta 1 plus beta upon differentiation with respect to time. Theta 2 dot is equal to theta 1 dot, because angle beta is a constant. In a rigid body, angle between this line and this line is not going to change, otherwise the body is deforming. So therefore beta has to be constant with time. Therefore theta 2 dot is equal to theta 1 dot and theta 2 double dot is equal to theta 1 double dot. Similarly, delta theta 2, that means change in the angle of this line, is same as delta theta 1. Thus, all lines on a rigid body in its plane of motion have the same angular displacement, the same angular velocity and the same angular acceleration. When a particle in a body moves from position A to B in a circular path like this, the particle A has gone from A to B. The angular displacement theta occurs. This displacement is a vector quantity since it has magnitude as well as direction. The direction is a rotation either clockwise or counterclockwise, and this is the distance s traversed by the particle. The rate of change of angular displacement with time is called angular velocity and is denoted by omega. Now, in this case, when the body is moving in the plane, that direction will be indicated by the normal. By convention, if the body is moving anti-clockwise, its direction of rotation will be in the direction of k, where k is a unit vector normal to the plane. If the body is moving in the clockwise direction, the direction will be in the direction of minus k, where k is the unit vector which is perpendicular to the plane. The angular velocity will have the same direction, that means clockwise angular velocity will be in minus k direction, anti-clockwise velocity will be in the plus k direction. Since all the bodies moving in a particular plane will have the velocity either in plus k direction or in minus k direction, angular velocity will be like that. Therefore, we generally omit k and instead we indicate the angular velocity by just either a positive number or a negative number. So, we can manage it by just algebraic addition and subtraction. The rate of change of angular displacement with time is called angular velocity and is denoted by omega. Thus, omega is equal to d theta by dt. The unit of omega in a SI system are radian per second. So, this is the rate of change of angular velocity with time is called angular acceleration and is denoted by alpha. Alpha is equal to d omega by dt. Angular acceleration, its units are radian per second square, or it is same thing as d square theta by dt square. You have to take double derivative. Also, alpha can be written as d omega by d theta into d theta by dt. That means this becomes d theta by dt is omega. So, it is omega into d omega by d theta. Therefore, if omega is expressed in terms of theta, then angular acceleration can be found by multiplying d omega by d theta and omega. When the particle moved from A to B, the distance travelled by it is s. This is like this. If r is the distance of the particle from the center of rotation, then s is equal to r theta and v is equal to ds by dt. That means this means this is r d theta by dt. Therefore, the linear velocity v is r times omega. We can find out the tangential acceleration. Tangential acceleration will be dv by dt, which is nothing but r d square theta by dt square. D square theta by dt square is equal to alpha, that is angular acceleration. Therefore, at is equal to r times alpha. Radial acceleration ar will be v square by r. Putting v is equal to r omega, we get r omega square. So, therefore, as the distance of a particle increases from center O, its radial acceleration increases. If the angular velocity is given in terms of revolution per minute, that is RPM, most of the machinery items or motors will be specifying the revolution per minute, that is RPM. Say motor rotates at 1450 RPM, like that. It can be converted into radian per second. Since there are 2 pi radian in one revolution and 60 seconds in 1 minute, the angular velocity omega is given by omega is equal to 2 pi n divided by 60 radian per second. Uniformly accelerated rotation. For uniformly accelerated motion with angular acceleration, at is equal to, we have dv by dt, which is equal to r d square theta by dt square. AR is equal to v square by r omega square. Now let us say d square theta by dt square is equal to alpha, which is constant. Now if you integrate it once, you get d theta by dt is equal to c1 plus alpha t, where c1 is the constant of integration. R omega is equal to c1 plus alpha t. Constant c1 can be found from the initial condition. If the angular velocity is omega 0, then at time t is equal to 0, omega is equal to omega 0, thus c1 is equal to omega 0 is equal to c1. Thus d theta by dt is equal to omega 0 plus alpha t. R omega is equal to omega 0 plus alpha t. This is the same way as you get equation of motion v is equal to u plus at. That is the. Now once we have established that d theta by dt is equal to omega 0 plus alpha t, now we integrate the equation with respect to time and say theta is equal to omega 0 t plus half alpha t square plus c2. This has been obtained by integrating the expression d theta by dt is equal to omega 0 plus alpha t, where c2 is a constant of integration. At time t is equal to 0, theta is equal to 0, giving us c2 is equal to 0. Thus, theta is equal to omega 0 t plus half alpha t square. Also, alpha is equal to omega d omega by d theta. Alpha can be written as omega d omega by d theta. Hence, alpha d theta is equal to omega d omega. Taking integral on both the sides, we get alpha theta is equal to omega square by 2 plus c3. Initially, at theta is equal to 0, omega is equal to omega 0, that means c3 is equal to minus omega square by 2. Thus, omega square minus omega 0 square is equal to 2 alpha theta, or omega square is equal to omega 0 square plus 2 alpha theta. These are equation of motion for angular motion. They are similar to linear motion along a straight line. Now that, so these are the equation of motion. One is omega is equal to omega 0 plus alpha t. Second is theta is equal to omega 0 t plus half alpha t square. This is like this. The third is omega square is equal to omega 0 square plus 2 alpha theta. So these are the three equations of motion. Now we discuss the another point. We discuss about the instantaneous center of zero velocity. Now for a body moving in a plane, we can find an axis normal to the plane about which the body may be considered to be in pure rotation. We can always find out a point about which body can be considered to be in pure rotation. This axis is called the instantaneous axis of zero velocity, and the intersection of this axis with the plane of motion is known as the instantaneous center of zero velocity. If a disk is rotating about an axis, then O is its instantaneous center, and axis perpendicular to the plane and passing through is called instantaneous axis of rotation. In this case, instantaneous center of rotation does not change with time. Now we will study the ways to find out the instantaneous center of rotation. Finding out instantaneous center of rotation is of some practical importance. For if you know the instantaneous center of the rotation of a body, you can find out the velocity of any particle by multiplying the angular velocity of the body with the distance from the center of rotation, and the direction of the velocity will be perpendicular to the line joining the instantaneous center of the body with the particle at that time. Of course, the instantaneous center may keep changing from time to time. Now, this shows a body in which there is a particle A and particle B. Instantaneous center is O. The particle A is at a distance of RA from the instantaneous center. Particle B is at a distance of RB from the instantaneous center. Therefore, the velocity of A is perpendicular to the line OA, and velocity of the particle B is perpendicular to the line OB. The magnitude of the VA is equal to omega times RA. Magnitude of B is omega times RB. So, therefore, the magnitude of the velocities are in proportion to the distance from the instantaneous center. In this case, the figure has not been drawn to the scale. Now, RA, so this gives us a clue to find out the instantaneous center of rotation. If you know that one body is moving and the particle A is having velocity VA, draw VA here. Similarly, particle is having velocity B, draw and show a velocity VB. Now, I can draw a perpendicular to the VA. Therefore, instantaneous center will lie somewhere on this line. Similarly, I can draw perpendicular to the VB, and the instantaneous center will lie somewhere on this perpendicular. Both these lines intersect at A, which provides us the instantaneous center of zero velocity. Now, if velocities of any 2 points A and B on the body are known, are not parallel, then this method is very handy. If there is a point about which A has absolute circular motion at the instant considered, this point must lie on the normal to VA through A. Similar reasoning applies to B, and the intersection C of these two perpendicular fulfills the requirement for an absolute center of rotation at the instant considered. Now, if the magnitude of the velocity of one of the points, say VA, is known, the angular velocity omega of the body and the linear velocity of every point on the body are easily obtained. because omega will be equal to VA by RA. Once you have found that velocity of angular velocity of the point, then after that it is very easy to find out the velocity of any other points. So, this is thing. Now, as the body changes its position, the instantaneous center also changes its position both in space and on the body. The locus of the instantaneous centers in space is known as the space centrode. If we draw the locus of the instantaneous centers in space, that will be known as space centrode, and the locus of the positions of the instantaneous centers on the body is known as the body centrode. So, this is the thing. Now, for the losing motion, suppose the body is undergoing losing motion, then the instantaneous center is at the point of contact of the roller with the ground. So, it is in contact with the ground. The velocities of points A, B and C are 0, omega r and 2 omega r in the horizontal direction. In the case of, if the body is not undergoing pure losing, that means there is a slipping also, in that case A will not have 0 velocity and therefore A will not be called instantaneous center. In this case, that this instantaneous center is changing its position. So, its space centrode is always in the straight line, because the position of A keeps on changing on the horizontal line. In the pure losing motion, the body is not having any relative motion with respect to the floor, and therefore A is instantaneous center. Now, let us discuss some other cases. Now, if a body is undergoing translation, like this, then like this, all the points on the body move with the same velocity. If we pick up 2 points on the body and draw lines perpendicular to the velocity of the point and passing through the point, the 2 lines will be parallel. Here one perpendicular line, one another perpendicular line. The 2 lines are parallel and they never intersect. However, we can consider that they intersect at infinity. Thus, the instantaneous center of rotation of a translating body is at infinity. The angular velocity of the body, translating body, is obviously 0, because any line in the body does not rotate. So, the rotation, its angle, there is no change in the angular position. So, a typical particle in the body has the magnitude of the velocity equal to the product of angular velocity and the distance of the particle from the instantaneous center. Thus, the magnitude of the velocity in the case of a translating body will be 0 times infinity, 0 into infinity omega r, which gives a finite velocity. The product 0 into infinity may mean any real number. Actually, the velocity is omega into r. If you say omega is equal to v by r into r, as r tends to infinity, this tends to finite velocity v. So, 0 into infinity can be considered as 1 also, it can be considered 2 also, like that. Thus, the translating body may have any velocity with 0 angular velocity and instantaneous center at infinity. In case you choose 2 points on the body on which the velocities are parallel but different in magnitudes. For example, this is the case. Now, in this case, you can suppose this is the instantaneous center, then the situation will be like this. The instantaneous center will surely lie in line passing through point A and also through B. Let instantaneous center be at a distance r(a) from B from A and a distance r(b) from A. Then V A by R(a) is equal to V B by R B, and also R A minus R B is equal to A B, the distance which is known to you. From these two equations, if you know the ratio V A by V B, you can determine R A and R B. Now, consider the case if the velocities of 2 points are parallel A is a point, velocity is like this, and B is another point in which the velocity may be like this. They are parallel but opposite in direction. Their magnitudes may be different. In that case, join AB, the instantaneous center will lie somewhere in this line AB. It will divide the line in proportion to the magnitude of the velocities. If you join the tip of the velocity vectors like this, here is the instantaneous center O. Therefore, V A is equal to omega times R A, V B is equal to omega times R B, or V A by V B is equal to R A by R B, where R A is the distance of point A from O and R B is the distance of point B from O. So, with this you can find out this thing. Finally, it is to be noted that only rotation causes the relative velocity between the 2 points in the body. In translation, the relative velocity between the 2 points in the body is 0. It can be easily shown that in a rigid body, the relative velocity between 2 particles of the body is in a direction perpendicular to the line joining the 2 points representing the body. For example, if there is a body and there is a point O on the body, let us say any other point A on the body whose coordinates are x, y when the axis system is passing through O. Therefore, in this case the distance OA is equal to x square plus y square. So, we have x square plus y square is equal to constant. Differentiate this with respect to time, you get 2x x dot plus 2y y dot is equal to 0, or x dot is equal to x dot by y dot is equal to minus y by x, or y dot by x dot is equal to minus x by y. So, we have got a relation like this, that this is a body O, this is a point A, now y dot is the Vy component of the velocity of point A. So, Vy and similarly x dot is Vx. So, Vy by Vx is equal to minus x by y, which is, if the direction of the velocity, suppose you have a velocity like this is Vy, this is Vx. So, the velocity is making an angle theta from the x axis. This tan theta is equal to minus x by y. The line joining OA, this angle is phi, so tan phi is equal to y by x. Therefore, tan theta into tan phi is equal to minus 1. This shows that tan theta is equal to minus cot phi is equal to tan phi plus 90 degree, or theta is equal to phi plus 90 degree. That means the velocity of the particle A is at 90 degree with the line joining particle A with the O. So, therefore, the relative velocity between any two particles of the body is in a direction perpendicular to the line joining the 2 points representing the particle. Now, we will carry out some simple examples based on this lecture. Now, if you are having a mechanism like this, there is a slider here, there is a slider here, join this by pin joint with a link, this one. So, this slider A and this is B, A can slide on the horizontal floor and B slides on the another, this perpendicular. Okay. Now in this case, if you have rod AB is joined by pin, you are required to find out the angular velocity of the rod AB. Now, how do we find out the instantaneous center of the rod? We know that the point A, which is on the slider as well as on the rod, is having the velocity only in the horizontal direction. So, therefore, this is VA. Similarly, another point B, which is on the rod, but since it is also on the block, it is constrained to move in the vertical direction. So, this is VB. Draw a perpendicular from VA. Draw a perpendicular from VB. These two lines intersect at point O. Therefore, the O must be the instantaneous center of rotation of the rod AB. So, instantaneous center of rotation has been found. Now, if you want to find out the angular velocity of the rod AB, it is simple. It is VA divided by OA. Omega is equal to VA divided by OA, or it is the same way that it is VB divided by OB. If you want to find out the velocity of any point C in between, this is nothing but omega cross OC. So, join O and C. So, velocity of C magnitude will be omega cross OC, and the magnitude of velocity of C is perpendicular to the line OC. So, this way you could have find out the instantaneous center. Consider a 4-bar mechanism where this is the one link which is fixed, another link, third link, and fourth link. One, 2, 3, 4. A, B, C, D. What is the instantaneous center of rotation of link 2? It is obviously at A, because all the time link 2 is rotating about 2. What is the instantaneous center of rotation of link 4? This is D. Now, how do we find out the instantaneous center of rotation of link BC or link 3? B has got a velocity which is perpendicular to AB. So it may have the velocity in this direction. C has got a velocity which is perpendicular to CD. So it may have velocity like this. Now these 2 points B and C are also falling on link 3. Therefore, in link 3 we know the 2 points at least B and C on which the direction of velocity is known. Draw the perpendicular to the velocities at points B and C on the link C. That is nothing but the extension of link AB like this and extension of link DC. Both extended meet at a point O, which will become the instantaneous center of BC. So therefore, in the 4-bar mechanism, you extend the link 2 and you extend link 4 to meet at a point O, that will be called instantaneous center of the rotation of the link 3. This instantaneous center of course keeps on changing with time. So this is thing about that thing. Similarly, let us consider this link. A, B, this is second link BC. This is again basically a 4-bar mechanism shown in a different way. Give angular velocity omega to link CD. Now when you rotate it like this, now you have assumed that the rod AB is vertical at the instant depicted. In this case, if you have to find out instantaneous center of BC, how do we go about that? Direction of BC is in this direction. VB is in this direction. So if you want to draw perpendicular to VB on the line BC, that is like this vertical, and this is horizontal. This is you draw a horizontal line passing through this one. So that means draw a vertical line here, draw a horizontal line here. This is AB. So these are meeting at this point. Therefore, this is called the instantaneous center of rotation of this one. Now, what happens if we make some variant of a 4-bar mechanism? Second, third link, and then you have got a slider. This is moving on a straight line. like this. Now, instantaneous center of rotation of this ring 2 is obviously at A, B, C. Instantaneous center of rotation of this rider is at infinity. You can draw a line perpendicular to the motion of this rider and say that instantaneous center lies somewhere at infinity at this line. Now, instantaneous center of rotation of BC at the instant the velocity of AB is in the vertical, B point is in the vertical direction. Therefore, we know that the velocity of point B perpendicular to that can be this is BC. So, velocity of that point B is along perpendicular. Therefore, on line BC, I will draw a perpendicular to the velocity which is obviously along AB. Similarly, here I draw perpendicular to the velocity which is along BC. These two meet at the point O. Therefore, in this case O is the instantaneous center of rotation. So, this is the thing about the instantaneous center of rotation. So, today I have discussed about the instantaneous center of rotation, about the plane motion and about the angular velocity. You can do the other numerical problems based on this lecture. For example, now if you know the angular acceleration alpha is equal to v minus omega minus k alpha. Let us say that in a typical motor, when you start a motor, you get a torque, and this torque is equal to, is proportional to I, that means K times I current, and this is K times VB, V applied voltage minus KB omega divided by R, where this is by kmf. So, that torque divided by moment of inertia gives angular acceleration. So, you get some expression for angular acceleration like this: alpha is equal to L minus k omega. If you get that, means its angular acceleration keeps decreasing as the omega increases. So, therefore, in this case, if you want to find out whether this rotating body will approach steady state motion or not, in this case it will attain the steady state at time t is equal to infinite, because this is d omega by dt is equal to alpha 0 minus k omega, and therefore you get d omega divided by alpha 0 minus k omega is equal to dt, or t is equal to ln alpha 0 minus k omega minus 1 by k plus c ln 1 by k ln c, where c is some constant. Therefore, this can be written as 1 by k ln c divided by alpha 0 minus k omega, or c divided by alpha 0 minus k omega is equal to e to the power kt, or alpha 0 minus k omega is equal to c e minus kt, which is exponential relation. At t is equal to infinite, this portion will become 0, and when alpha 0 will be k omega, that means the final velocity will be reached, and that time the angular acceleration will be really 0. So angular acceleration alpha at any instant is a c e minus kt. So therefore, in this case, the angular acceleration becomes 0 at infinity. So like that, number of numerical problems you can solve based on the lecture. In all these things, you may have to use the differential calculus.